Welcome. It's just gone 7 p.m, Wednesday the 23rd of June, and you are watching Regional Wrap. This is episode 12. Regional Wrap, providing an insight to the issues affecting regional Australia and giving a voice to regional residents. My name is Bill Bates, and joining me on this episode is my guest, Dr. Robert Fagan, a geologist of more than 40 years, with more than 20 years lecturing in all aspects of geology at the West Australian School of Mines and Curtin University. He has a PhD in geology and geochemistry. He has run extensive courses on various aspects of geology, study of the Earth's history, the general public and industry. The study of the Earth's history includes climate, atmospheric history and evolution. Dr. Fagan is an author of a recently published first-year university level textbook on geology, Understanding Geology. Welcome, Robert. Would you start with telling us a little bit about your younger days and what led you into a lifelong career in geology?
Well, my younger days, I got interested in geology at about the age of 13 or 14 because I went on holidays with a great uncle in New Zealand, where I'm from originally, who was a prospector in the goldfields of Central Otago. And he took me out gold prospecting there in the old gold areas of Central Otago. And we found gold, and he showed me all the interesting ways of looking for gold, and I got interested from that point on. I became a prospector, basically, an interest in prospecting from about the age of 13, which has continued all the way through to the present. But that then motivated me when I went to university to do geology, and then I became a geologist from that type of origin.
Now, in those days, was that considered a nerdy career or just a steady type of employment?
It was regarded as a fairly serious career, and I was very interested in Earth history and geology anyway, before I knew a great deal about it. And when I did first year level geology, it really fired me up at university to complete my degree in that subject. When I first went to university, I could have done chemistry or a few other subjects, biology and so on, but I then followed through after doing first year geology.
And what about the first career moves?
I graduated with an honours degree in geology from the University of Otago in New Zealand, right at the end of the nickel boom. And jobs just basically faded away, and I was unemployed. And I was actually digging drains locally in the town that I lived in. And the only job I got was I applied for a teaching fellowship at the University of New England in Armidale, New South Wales. And that basically meant that I would be a tutor in geology classes half the time. And the other half the time, I'd be required to do a PhD, which I did. And so that was the only employment opportunity I had after applying for about 40 jobs with mining companies. There were no jobs going. So I was forced into the academic life by that process. So I did a PhD at the same time as earning a living tutoring in geology classes.
So without being in the mines and stuff, that is there sort of demarcation between geology people, like the people who teach and the people who do, like you often hear?
Well, there's two aspects of geology, really. There's the academic pure science aspect, which is the sort of geology that I've been doing. But most graduate geologists end up working in industry, particularly the mining industry. And so that just uses part of the geological education that they've received, but mainly using it to find ore deposits. But the other group of geologists who graduate are more interested in pursuing the pure science, and they tend to do higher degrees, particularly PhD degrees, and end up in academic environments or museums or CSIRO type positions, government research organisation positions. So there is a dichotomy. There's the mining geologists versus the more academic geology people.
So how many students you think over your lifetime have gone through your classes?
Well, I've taught geology for 40 years, and I've probably taught thousands of geologists. Most geologist graduates, but I also teach people who only do first year level and then go on in other biology and chemistry and so on. But of career geologists, I've probably taught several thousand over 40 years.
Okay, we'll probably move on now to the topic of the night in regards to, and it really does deal with the geological time scale and what was happening with it, with our little planet, our little delicate petal of a planet that people are so worried about. But we can go back and we can, and your field can show you what a devil of a time it had during its 4 to 5 billion years lifetime. It's not such the soft pedal that a lot of people claim it to be.
Yes, so this is the first of 2 talks that I'll be presenting. The next one will be next Wednesday. But this particular talk is basically about the geological nature of Earth's climate. It's the geology side of climate and its evolution. Next week, I'll get more into the greenhouse type narratives of climate change. So this talk will be mainly on the geology. But before I get into that, I really need to put geology to some extent into context a bit before I get on to the actual geology. And the first thing I need to inform people about is, what is geology? I don't want to go into a lengthy explanation here, but geology isn't looking at rocks. It isn't the study of rocks. It's the study of Earth history. That's what geology is all about, the study of Earth history. And we do that by getting information from the rocks. And the next thing I need to explain is, how do we determine Earth history? Now, to a geologist, rocks are like books. If you can't read, then all books look the same and of no particular interest. But if you can read, the book tells you a story, and it's the story that's of interest, not the book itself. In geology, we are taught, or we teach, how to read the story contained in rocks, and it's that story that's of interest. And how do we sort of determine that? Well, there are lots and hundreds of different rocks, but each individual rock has a different means of formation. And just about every rock that's in existence is forming somewhere in the world today. And we can see where these different rock types are forming. We can see sands washing up on beaches to form sandstone. So we know how sandstones form. We can see coral reefs developing to produce coral. And we can see ancient versions of that coral. And so we know the environment that those ancient corals formed in. We can see molten rocks pouring out of volcanoes and producing rocks like basalt. And we can see basalts all over the world of different ages. And we know when we recognize the basalt, how it formed, because we could see them forming today. So that's how we put together that history. And at this point, another concept that I need to introduce, which I'll have to bring up an illustration for, which I'll do at the moment, which is the one you should see on your screen now. The layered nature of the Earth. The top left illustration there shows a cutaway section of the Earth, showing its very layered structure. And I just want to very briefly comment on the layers. The interiormost layer is the inner solid core, made of metal, iron, and nickel, about 80% iron, 20% nickel. It's made of stainless steel, essentially. Then there's an outer zone there, which is a liquid iron core, liquid equivalents of the inner core. Then there's an extensive zone, which is labeled the mantle there. That's made up of basically magnesium and silicate rock. And then there's another outer layer, very thin layer at the edge, which is called the crust. And that's made up of a different composition of rock. It's made up of sodium, potassium, aluminium silicates, and it's very thin. Then there is another layer on this illustration, which I'm trying to highlight now with the mouse pointer, and it's called the hydrosphere. And that's the layer of liquids, mainly liquid. The only liquid that's important is water, and it's largely the sea. So that's called the hydrosphere. So that's another outer layer. And then the next layer out, and the final layer, is where all the gaseous components of the Earth accumulate. And that's the atmosphere. And it's the atmosphere where all the climate occurs. So that's basically the structure of the Earth. And we're going to be concentrating in these discussions on the atmosphere. Now, the atmosphere is actually visible. If you go up into the outer space there, in the top right-hand illustration there, you can see a photograph from a spacecraft where we can actually see the atmosphere. There's a light fuzzy zone extending from the Earth's surface up to the black zone. The black zone is where there is no gases. There's no atmosphere. That atmosphere is about 90 kilometers thick. And that's very important for the discussions we're going to be having today and next week. The present atmosphere of the Earth is displayed there, is made up, as the pie chart shows in the lower left there, almost 80% nitrogen and about 20% oxygen. And there's a few other components. Argon is the next major one. And then ones we're interested in particular are carbon dioxide, which is about 0.04%. Now that's the present composition of the atmosphere, but that wasn't the original Earth atmosphere. The original Earth atmosphere is depicted in the little table on the lower right there. The blue coloration that I'm highlighting with the mouse pointer is the present atmosphere of the Earth, the 80% nitrogen, 20% oxygen, etc. The next column over, which is the sort of fawn color, is the original atmosphere of the Earth, which was very, very different. The original atmosphere of the Earth only contained 2% nitrogen rather than the 80 we have at the moment, contained no oxygen, but contained 98% carbon dioxide. It contains virtually no carbon dioxide at the moment. That early atmosphere was incredibly thick and very heavy. It was about 100 times heavier than our present atmosphere. And if we were standing on the Earth way back in the Archean, when that atmosphere was in existence, we would have absolutely been crushed to death by the weight of the atmosphere. It would be the equivalent of being 2 or 3 kilometers under the sea. That would be the weight of that atmosphere. Now you can see this very early atmosphere is quite different from the present atmosphere. But this very early atmosphere is exactly the same as the present atmosphere we see on Venus, which is illustrated in the third column of that table. It is exactly the same atmosphere on Venus that the Earth had in its very early stages. But the Earth completely lost that atmosphere. Where did all that 98% carbon dioxide in our early Earth atmosphere go? It was basically drained out of the atmosphere over time to dissolve in the ocean, and then the carbonate from that reacted with calcium dissolved in the ocean to form calcium carbonate, which is limestone. So that 98% carbon dioxide in the early Earth atmosphere is now completely tied up in all the limestones and limey rocks of the Earth. It's been completely removed. And what we were left with, the nitrogen then went up from 2% to 78%. And later on, when life started to develop, we started to produce oxygen, and that was introduced. So those processes didn't happen on Venus. Venus didn't lose its original atmosphere. And the reason it didn't lose that original atmosphere is that it didn't have any oceans. It was the ocean which drove this chemical fractionation or chemical screening of carbon dioxide out of the Earth's early atmosphere. So that's a fairly dramatic early start. Where did all these gases originally came from? When the Earth originally formed, it was molten, entirely molten in its early stage. And all these gaseous components, including water, H2O, were...
Want to pull that screen down, Robert?
Sorry?
Can we pull that screen down?
You can if you like.
No, you have to.
Just go back to, yeah. So you're seeing me now?
Yep, thank you.
Yeah, so I just lost the thread there a bit. So basically, the carbon dioxide has all disappeared into rock. And I might say that limestone by weight is 50% carbon dioxide. Half the weight of a limestone almost is purely its carbon dioxide component. So that's where it basically all went.
So an interesting thing out of that conversation also is that Venus never had any oceans, but we did. So can you give us a bit of an idea where our oceans come from?
Well, Venus probably did have oceans. Venus is an exact duplicate of the Earth, but it's had a different history since its original formation. And Venus originally had as much water in its chemistry, if you like, early chemistry, as the Earth had in its chemistry. But that has, and that water would have probably come out in the same way as it has on Earth, but Venus was very much hotter, and that water boiled. It was not liquid water. It was in the atmosphere and couldn't condense into liquid water. And over time, that component of their atmosphere, the water component of the atmosphere, was lost. It was too hot for it ever to condense into an ocean. So that's why the difference is there. Venus didn't have an ocean, the Earth did, and that makes a very big difference in that history. So what I now want to do is just move on. And I want to talk again, a bit of context here, is the nature of the planetary gases and climate. Now, the moon is the same distance from the sun as the Earth is. And at night, the moon has a temperature of minus 190 degrees centigrade, minus 190. Very, very cold. But in the day, it's very, very hot. It has a daytime temperature of 130 degrees centigrade. So this means it has an average temperature over 24 hours of minus 60 degrees. So the moon is average lunar temperature is minus 60 degrees. Now the Earth, if we stripped the entire atmosphere off the Earth and left it where it is, the Earth where it is, it would also have the same temperature as the moon. The average global temperature would be minus 60 degrees, roughly. Very, very cold. Much colder than we're experiencing at the moment. If you then replace the atmosphere of the Earth back to the Earth, but remove the greenhouse gas components, which are mainly about 3 or 4% water vapor and carbon dioxide and methane and a couple of others. So if you replace the Earth's atmosphere, but don't replace in it the greenhouse gas components, it's been calculated that the Earth's average global climate would then be minus 18 degrees. The average global temperature would be minus 18 degrees, extremely cold, cold enough that all water would be frozen, for example. But if you then replace that greenhouse gas component, the 2 or 3% of water vapor, water gas, the carbon dioxide and the methane and so on, put it back into the Earth's atmosphere, we get the present atmosphere of the Earth, and it has an average global temperature of 15 degrees centigrade. So you can see from that summary there, you might have to carefully think your way through that a bit, but the greenhouse gas component of the Earth's atmosphere contributes 33 degrees by itself to the Earth's global average temperature, bringing it up from minus 18 degrees to plus 15 degrees. So that's a remarkable contribution that it's adding to the atmosphere. And that's one of the reasons that climate scientists in particular are so worried about things like the greenhouse gas component, because if you increase it, it will increase the temperature. And if you decrease it, it is likely, in their view, to decrease the temperature significantly. And that's the sort of major concerns that in part is driving the greenhouse gas debate in terms of climate. So that's a bit of background information that we need to have as a bit of a context for what I'm going to talk about next. So I'm going to bring up another slide here. And where are we there? This one here. And we're going to look at how the Earth's climate has evolved over time. And we've got basically here a geological time scale chart. And I might just bring up a change here in my pointer. Where are we there? So we can see things a bit more clearly there. Here's chart, basically with time starting at the very beginning of the Earth at 4.6 billion years or 4,600 million years ago down at the bottom, and time is progressing up with the numerical values changing up until the present. And the present time we're experiencing at the moment is right here at the top of the chart. And there have been a number of numerical values of time in terms of hundreds of millions of, or millions of years displayed along that axis. Next, in the next column here, we have labeled periods that geologists have assigned, particularly in the past, before we had much numerical dating information, for periods of time. And some of those names, for some of you people, would be familiar. The Carboniferous, the Permian, the Jurassic, and so on. They're just labeled intervals of time that are used less these days because we've got numerical information, which is often more valuable. Now, an important thing to notice about this chart is that the time scale going from 4,600 million years at the bottom up to the present time is not an arithmetic regular time scale. It's been contracted in some parts and expanded in others. And the reason this is necessary is if we made that a linear scale of time, that chart would have to be 3 meters long, and we couldn't display all the information on it in any meaningful way. So what's been done on this chart is to vary this time scale in various places, compressing some parts into shorter spaces and expanding other parts of interest. And as an illustration of what's happening here, you can see these red arrows down the margin here. The bottom third of this chart, going up to roughly where I are there, the bottom third of that chart represents 90% of all geological time, is compressed into that zone. The next third of this chart, going up to about here, is 8.5% of all time in that interval. And the last sort of third, if you like, of the chart up here represents only 1.5% of all time. So we can see there's been a variable compression of various parts of the climate scale here to make this chart as useful as possible and to draw as much and present as much information as possible on it in a meaningful way. Just have a bit of a sip here. Now, if we move over to the next couple of columns here, which I'm highlighting with the pointer, at the top here it says this column here is mean global temperature. It's displaying how mean global temperature varies across time for the Earth. The present mean global temperature, which is 15 degrees centigrade, is actually located where the pointer is now at the top of the diagram, between where it says cold and warm. So anything to the left of the pointer is colder than present, and anything to the right of that pointer would be warmer than present. And so we've now determined what the temperature of the Earth has been at various stages in its history, and we've traced it. And I'll just trace back to the start down here at the bottom, 4.6 billion years ago, and the temperature of the Earth at that stage was, just one other point I need to make here. This is the present temperature of the Earth, and this line that I'm following down here, this very sharp line, is a trace of that 15-degree present global average temperature. It's just showing you where that global average temperature of 15 degrees is located on this illustration. If we then go back to the very early Earth here, the temperature is roughly out here. We can tell this by observations we can make in the rock that give us very good indications of how the temperature has varied and what the temperature was at various stages. So back at the earliest stages here, the temperature here, where my mouse is at the moment, was quite a bit higher than the present day global average temperature. But as time progresses, and we're moving up time now, the temperature lowered a bit and then dramatically lowered where I am at the moment, got back to 15 degrees here, the present global temperature, and then dropped below that. So it got actually colder than the present temperature. And that was the first glacial episode that we have in Earth history, as represented by that little blue coloration there. It then warmed up back higher than 15 degrees and then cooled down again to below 15 degrees, the present temperature. And we got another glacial episode in there, that blue. And it keeps on doing this. So it warms up significantly higher than 15 degrees. cools down and we have a glaciation below 15, then comes up and goes down, and I won't keep repeating all this, but all the blue indications there are locations in Earth time when the temperature was very much colder than present day global temperatures and there was a glacial event. And then we come up to a much warmer period over here, quite a bit warmer than the 15 degrees, and comes up to about the present. And up here in the Quaternary, as it's listed here, is where we descended into the most recent Pleistocene glacial event, represented by this zigzaggy pattern there. So that coloration, or that line, shows you how the Earth's temperature has varied over time. Now, there's a couple of important things to say about this. For most of Earth history, the Earth temperature has been warmer than today and several degrees warmer than today. This temperature range from about here at 15 degrees, the present temperature, up to say there, is probably about 4 or 5 degrees warmer than today. So for almost 90% of Earth history, the global Earth temperature has been about 3 to 4 degrees warmer than at present. And it's only for about less than 10% of Earth history that the Earth temperature has been colder than present day temperatures at about 15 degrees average. And they have all been periods of glaciation in the Earth. Now you can see here there's a dashed line that I'm highlighting with the mouse pointer now up here. That's a sort of an average global temperature for the Earth over time. It's running through the middle here of these warmer events. And it's suggesting that over 90% of Earth's history, the Earth climate has been 3 or 4 degrees warmer than today. We're in part of the coldest periods of Earth history outside of glaciations. And that's important to keep in mind. It's showing us that rather than present climatic conditions being the norm, they are very much not the norm. They're colder than the norm. They're about 3 or 4 degrees colder than what the temperature would normally be through most of Earth history outside of glaciations. Now, just another thing on the right-hand side here, I won't discuss this much because it's not that relevant. It's a similar sort of illustration that we had for temperature, but it's for mean global precipitation. And the present global mean precipitation is where the mouse pointer is now, between where it says dry and where it says wet. And this reference line of the present day average global precipitation runs down through the middle there. And when we're to the right of that line, as we are here and here where the green areas are periods of time when the Earth has been very much wetter than today. And then when we're to the left of that reference line of the present condition, where we've got the brown zones here, it's periods of time when the Earth has been very much drier than today. And you can see that in Earth history, there have been numerous periods where the Earth was very much hotter, very much wetter than today, all the green areas, and equal numbers of pretty much of periods of time, lengthy periods of time often, where the Earth has been drier than today. So when we put these two charts together here, the temperature and the precipitation temperature, we can see that throughout most of Earth history, the Earth has been significantly hotter than today. But some of the time it's been hotter and wetter, like there, and some of the time it's been hotter but drier than today. But through virtually all of geological climate history, the Earth has been hotter than today by about 3 or 4 degrees. That's a fairly...
On that graph, I think a lot of people with obviously all the Jurassic Park movies and that, we envisaged at that time when the dinosaurs were running around, it was obviously hotter, but most people would have thought it would have been wetter because the scenery is always in sort of jungle and all that sort of stuff. So
yeah, the dinosaurs were in existence.
So how did those sort of animals survive if it was drier or sort of from our perception we get from silly movies.
Overall, the Earth was drier, but it wasn't dry everywhere. And so there are parts of the Earth now that are dry, but there are other parts that are wet and more vegetated. This is a global sort of average. So there would have been regions of the Earth where there were high rainfall or higher rainfall and more vegetation. But most of the Earth wasn't like that. It was actually drier. And we know that these conditions were drier because in this zone here where it was drier, the rock sequences that we see are all rock sequences that form in desert environments. Desert sands or what were the equivalent of desert sands and desert environments in the past. And the vegetation fossils that we see are all dry vegetation fossils. There was vegetation there, but there were vegetation that favoured dry areas, not lush vegetation. So that sort of image we have of the dinosaurs running around through thick vegetation is not realistic. The area where the vegetation was most dramatic is here, which is the Permian Carboniferous, where all the coal deposits originate from. This was an absolute explosion of vegetative life, and that matched up with having a cold climate, but having a very wet climate. So cold, wet climates are where vegetation really takes off. And that combination of cold and wet that occurs there is the only combination of cold and wet, really, that occurs in most of this time scale. And that's why we get most of our vegetation and fossil remnants of that vegetation and coal deposits, etc., in that particular environment. So, I've made a number of points there. I just want to go on, if I can, to the next illustration. Now, it's a similar diagram, but it's arranged differently. This time, the time axis in the previous diagram ran from bottom to top vertically. In this case, the time axis runs horizontally from left to right. And at the left-hand part of this diagram is the beginning of the Earth, 4.6 billion years ago. And this is the present time here on the right-hand side of the diagram with the present temperature, global 15-degree temperature condition. And that reference line through that present-day global temperature runs through there, and everything above that line, which is coloured orange, is where it's warmer than today, and everything below that line, which is coloured blue or light blue, is conditions where the Earth was colder than today. And we can see it was mainly warmer than today, significantly warmer through all this period of time there, dropped down a bit here, and this got colder than today, produced a glacial event, warmer again through here, another glacial event, and so on. So it's repeating what we saw in the previous diagram. It's just arranged in a slightly different way for a point I want to make in a minute. The dashed red line running through here that I'm following with the mouse pointer now is basically what the average global temperature was for those periods of time. And we can see that the average global temperature was 2 or 3, 4 degrees warmer than the present temperature. And sometimes it got quite a bit warmer, perhaps, than that. So again, it's showing that the mean global temperature is warmer conditions than today. But the other point I want to highlight in this particular diagram is if you go to this point here, you see there's a red dot there? That's the present climate, the present day environment. That shows you exactly what the present day climate. If we now look in this chart to see everywhere else in this climate history, was the climate exactly the same as we see today? So here's today's temperature. So there's a red dot showing that. The next time in this chart where the Earth was the same temperature as it is today was that point. And the next, and before it descended into colder conditions and then came back. And again, at that point, we get the same temperature conditions that we see today. And it happens again and again where these red dots. So we'd like to think that the present day global temperature was long lasting and pretty persistent. It wasn't. It was a very minor event that happened several times during Earth history as we descended from warm conditions into glacial conditions. or we come out of glacial conditions into warmer conditions, so that the present day global temperature is a complete aberration in the temperature history of the Earth. It's a very minor event or minor occurrence in there.
And we're very fortunate to live in it.
Well, we are living it, but it may be minor, but it does. We're going to talk about more of this next week, but it does extend for millions of years, even though it's still a minor component. So we'll get back to that point in a later part of these talks. Now, what controls the Earth's climate anyway? And here's an illustration of this. Here's basically the Earth, and here's the sun. And the sun is basically pouring out over 4.5 billion years, pretty much, not entirely, but pretty much a constant amount of heat, radiating it out into space. And the Earth, oops, hang on, I've just got to go back here. The Earth here has been pretty much fixed in space. That's a constant distance between the heat source, the sun, and the Earth. Now, if that sun is constant in heat output, and the distance between the Earth and the sun is constant, then the Earth should have a constant climate. It's getting a constant input of the same amount of heat over a very long period of time. I've also got in there a bit of an axis tilt has an effect. And so basically the Earth, if there's an equilibrium between the Earth-Sun system, that's basically illustrated in this diagram. There's constant heat put resulting in a constant mean global temperature overall. Now, this isn't strictly true, because that distance between the sun and the Earth isn't constant, because the Earth's orbit isn't circular. If it was circular, it would be constant. But because it's elliptical, there are some periods when the Earth's a bit further from the sun and we get less heat, and that's winter periods, and other parts of that ellipse are closer to the sun, gets more heat, and that's where summer is. But this shows you basically the relationship of the Earth-Sun thermal equilibrium system here. And we need to keep that in mind. It helps explain why we have the climate we do to some extent. So here's another one of these diagrams of I'll speed up on this one, of time versus temperature. And it's the temperature, the time axis is from the left, the beginning of the Earth up to the present time. And the red line here is showing how temperature has varied over time. Now, we've covered most of that, but we can see the dashed line there suggests that for large parts of Earth history, the climate has been pretty much, the temperature has been pretty much constant. This is the present day temperature down here. And this is the present marker, if you like, of present day temperature conditions. So for most of Earth history, it's better illustrated on this diagram than the previous ones, the Earth has been significantly hotter by 3 or 4 degrees, possibly more, over large periods of time, except for the blue areas under here, very short periods of glaciation. Now, another thing that I want to show on this diagram is the blue line. You can see the blue line that runs through here. That is a measure of the atmospheric composition in terms of carbon dioxide. And the carbon dioxide scale is the blue one here. So at the moment, we're down here at the right-hand present axis here, where the carbon dioxide content of the atmosphere is about 400 parts per million. But over in the past, it was very much higher. And we follow these blue lines around, and we can see that it's been decreasing overall. And if I move to the next diagram here, which is it's the same diagram without the coloration, we can there see perhaps more clearly how carbon dioxide has varied over Earth history, getting way back towards the Archean and certainly into the Precambrian 600 odd million years ago. We can see that the carbon dioxide content of the atmosphere there was about 2,500 ppm looking at this scale. But over time, we can see that it's sort of decreasing progressively over time. And there was a very big dip in it here. And that is because that's where we had the vegetation explosion where trees occupied the land, pulled huge amounts of carbon dioxide out of the atmosphere to produce trees and vegetation, and pulled it down very sharply, and then it began to slowly come back, and then it continues to decrease over here. Now that blue dashed line there shows you how the Earth's atmospheric carbon dioxide has decreased almost linearly and progressively and dramatically over time, over Earth history. Basically, where we are at the moment here at about 400 odd ppm, we have lost over 90% of all the original carbon dioxide, which was only 3,000 parts per million anyway, at the beginning of the Archean, over time. It's been a progressive linear decrease that is basically unwavering, except for a couple of dips where vegetation explosions occurred. Now that's very dramatic. And that decrease in carbon dioxide is due to the fact that the Earth is not sufficiently warm to prevent the oceans being cold enough to suck more carbon dioxide out of the atmosphere. That linear decrease in carbon dioxide over time is because carbon dioxide is more soluble in the ocean, and it's being pulled out very, very slowly, not huge amounts, but very millions of years, progressively out of the atmosphere. And that is removal of carbon dioxide from the atmosphere has got to about 300 or 400 parts per million at the moment. And if that process would continue, which it likely would do, in another 100 million years, there would be no carbon dioxide in the atmosphere. It will have all been pulled out and into the ocean and ended up ultimately in limestone. Without carbon dioxide in the atmosphere, all life would cease on Earth. All life is dependent on carbon dioxide. That's where the vegetation gets its major components from, carbon dioxide. And animals get their carbon dioxide by either eating vegetation or eating other animals that eat vegetation. So there is a one-way progressive linear decrease of carbon dioxide over time. And it's getting to the stage now where it's starting to become concerning. It's so low now that plants are actually, and I'll talk about this more next week's session, plants are starved for adequate carbon dioxide. Their growth is stunted. If we want to produce flourishing plants, we have to introduce extra carbon dioxide into greenhouses, and the plants then flourish because they have greater access to a very significant ingredient for their existence. So
Plant food.
Sorry?
Plant food, carbon dioxide.
Yeah, well, it's food. Every living thing that has ever existed has got all of its carbon from carbon dioxide in the atmosphere, but we're starting to deplete it very seriously. So that's a fairly dramatic thing, which we'll get back to in other portions next week of this discussion. So I just want to sort of start to wind up a bit here. So that's given you a sort of a general overview of both how climate has changed in the geological history of the Earth over basically 4 billion years. And it's also showing you how a major gaseous component of the atmosphere, carbon dioxide, has also changed. So if we look at the temperature change over time, it's largely been constant, hasn't varied very much, but it's been warmer than today. The carbon dioxide has decreased dramatically and fairly linearly over time. And the carbon dioxide trend is not matching the temperature trend. They're quite different. They're behaving independently of each other. And the carbon dioxide loss that we expressed here in that previous illustration with the blue curve is not affecting the temperature of the Earth. It's decreased 90% over the last billion years, but it hasn't changed the average global temperature of being 3 or 4 degrees warmer than today over that same period of time. And that's a fairly interesting phenomenon. What we want to talk about next week is a little bit illustrated in this diagram. We're now going to just look at the most recent part of the geological history of the Earth. We are going to look at the last million years, the Pleistocene glaciation, but more importantly, the Holocene, which is the last 10,000 years, the interglacial period, because that's where the climate that we are currently exposed to has basically developed. And this diagram that we have got on illustration here is again a timeline diagram from about 400,000 years here, not very far into the distance, up to the present. And it's showing how carbon dioxide has varied in the atmosphere over that interval. And this information has basically been derived from ice cores, from the Arctic and Antarctic. Deep ice cores allow us to drill down several kilometres and sample ice over that particular interval of time. Going back actually about 800,000 years, we can sample ice. That ice has bubbles frozen into it, and those bubbles contain the samples of the atmosphere that existed at the time that those bubbles form. And they tell us what the atmospheric composition was at those times at various stages here in terms of carbon dioxide, because we can recover the gas from those bubbles and analyse directly its carbon dioxide concentration. And we can also work out what the temperature was at each of these samples, because those bubbles contain water. And the water is made up of H2O, and oxygen has two isotopes. It is oxygen 16, which is a light isotope, and there's oxygen 18, which is a heavier isotope. The difference being that oxygen 18 has two more neutrons in its atom than oxygen 16. Now that difference from 18 to 16 is a weight difference, and that affects the way that that oxygen ratio is preserved. When things are hotter and easier, the lighter isotope gets enriched. The 16 becomes more dominant. When things slow down, the heavier isotope separates out, and we get a different ratio. So that ratio between oxygen 16 and oxygen 18 is a direct function of the temperature. And so when those bubbles from the ice cores, we can analyse the oxygen 16 and 18 ratio and directly correlate that with temperature. So on the illustration we have here, that's just carbon dioxide. And if we look at the pattern, you can see it's a sort of zigzaggy sawtooth pattern. At the left of the diagram, it climbs up to a peak somewhere about here, then drops down. And then climbs up again, gets higher, then drops down. Climbs up again, then drops down. Climbs up again, then drops down. At the moment, it's climbed up to there, and we would anticipate, all other things being equal, that it would start to drop down into the future, just like as it does in the previous patterns that we see there. Now, those patterns illustrate there's a cyclical behaviour pattern going on here with carbon dioxide enrichment. And if we can look at that pattern there, that's 100,000 years long, roughly. And from that peak to the next peak is another 100,000 years, and to the next peak, another 100,000 years, and the next peak, another 100,000 years. So this cyclicity of behaviour is recording 100,000 years cyclical events when CO2 is rising or decreasing. Now, if we get over to the right-hand side of the diagram, this is basically where we are at the moment. But carbon dioxide has now decided to do something very different from that pattern. It's gone up to here. And it's gone up to here because it should have dropped away down here, but it's gone up to here because that component of carbon dioxide is not natural carbon dioxide, it's man-made carbon dioxide. It's gone up dramatically over this very short interval as a result of carbon dioxide production during the Industrial Revolution up to the present. That's man-made CO2. That's why it's gone up. It's not related to this pattern, it's the man-made contribution. Now, if we go down and look at the next diagram here, it's exactly the same diagram, pretty much, slightly longer period of time, but again, pretty much the same. And in this diagram, the blue curve here is exactly the same as the curve, the carbon dioxide curve in the previous diagram. So it's the same information, and you can see the zigzag pattern. But what's also recorded on this diagram here in the red curve is the temperatures that were recorded. And you can see that the temperature very closely follows the carbon dioxide, very strong correlation here. And this is part of the reason that climate science in particular has decided that carbon dioxide has been a driver for temperature and driver for climate. The temperature has increased as carbon dioxide has increased because of the greenhouse effect. And they are interpreting it entirely in that way. And next week we'll discuss this a little bit more. But the alternative view from the skeptics is that the carbon dioxide is increasing following the temperature, not the other way around. And it follows the temperature because as the global temperature increases, solubility of carbon dioxide in water decreases. And so some of the dissolved carbon dioxide in the sea is bubbled out back into the atmosphere. And that causes an increase in carbon dioxide driven by the temperature, not the other way around. When we get over to the right-hand side of the diagram here, this is the man-made component here from the Industrial Revolution. There isn't an increase, and this is often used to put the fear of death into people, to suggest that the temperature, if it's being driven by carbon dioxide, is going to rocket up here exactly the same way as it rocketed up here as CO2 increased. Now we can tell that the temperature difference between there and here, which is about the same as the different distance from there to there, is about 8 degrees. And it would suggest if we were going to recreate the same thing, that the temperature would increase by 8 degrees, which is not likely to happen. So we're going to rediscuss some of this in next week's talk. And just the last slide to finish up on here, this is the diagram, an exploded diagram of basically the Pleistocene and the Holocene period of time, where temperature is shown here. And again, the scales are greatly expanded over here relative to there. And this is where we are at present. And this is recent warming periods, the medieval optimum. In here somewhere, we've got the Roman optimum and that little bump there, and we've got the Holocene maximum in here and so on, and other ones here. And then we get into the Pleistocene proper, and we have little warming pulses as well. If we took this scale here and contracted it to the same scale as here, this whole region here would end up looking a little bit like that there. And we can see that we've experienced these cyclical warming events 15 times, basically in the last 1.5 million years. And they're likely to be repeated. So they're not a novelty. The Earth has been in these positions before, many times, 15 times, and then recovered. So these are the zigzags that we saw in the previous illustrations going there. And this is the present zigzag in here. So we might leave things at that point at this stage, and we will revisit some of these issues in a bit more detail with a bit more explanation of what's going on for the last 10,000 years or so in the talks.
Just before we drop off there, does anyone have any clue what the trigger points, what causes these trigger points into the temperature and to change direction?
Yes, they do. And I'll just go back to this this earlier diagram here, this one here, because it's probably clearer to see there. You can see that there's a trigger points here going up and down and up and down. So the atmosphere gets more CO2 rich quickly, and the temperature rises quickly and then decreases slowly, then rises quickly and then decreases slowly at 100-year intervals. The reason for this is due to, in this particular case, that 100,000-year interval is due to what's known as Milankovitch cycles. And they're regular cycles in the way the Earth orbits the sun. And sometimes it extends into a more elliptical orbit, and things cool. When that happens, things drop down here. And then that elliptical pathway or orbit of the Earth around the sun shrinks a bit. And so the sun gets, the climate gets warmer. So each of these highs is one of the Milankovitch cycles. So at this point, the Earth is closest to the sun in that the length of its ellipse. And that point here, the Earth is furthest from the sun in terms of its ellipse. And at every 100 years, that global ellipse, and I'll just get back into the vision here, that ellipse of the Earth around the sun is longer and colder and shrinks and becomes warmer, and that happens every 100,000 years. And there are other couple of repeating features such as rotation axis as well that come into play. So it's controlled by Milankovitch cycles, and that's basically controlled by the diameter of the Earth orbit ellipse around the sun, increasing or decreasing.
And some of those variations, like they're slightly out of sync. The orbiting time period is out of sync with the change in the angle of tilt. I think the angle of tilt changes about less than 2 degrees, and so we can't. That's probably why we get some variation in.
Some of those other little bumps there. The major sawtooth is due to that 100,000 year cycles, but every 40,000 years, the Earth's rotation axis, which is 23 degrees now to the axis. It varies. It gets more or less, and that means that parts of the Earth, because of the tilt, are either closer or further from the sun, and that happens every 40,000 years. So there's another change every 40,000 years, reflecting the thermal or temperature effect of that. And then another thing that changes every 20-odd thousand years is that the rotated or inclined axis of the Earth rotates. So it not only shifts over 23 degrees, but it starts to spin as well, produces a wobble effect. And that introduces more climate variations as a result of that. And all of these three events, all of which are called parts of the Milankovitch cycles, the 3 cycles, superimpose. Some are at 100,000 years, but every 40 years on top of that, there's the axis change, and every 20-odd thousand years on top of that, there's the wobble effect starts to have an effect, and they all start to interfere with one another. So that sawtooth pattern that you saw has got lots of little smaller irregular peaks within it that reflect some of those variations. Does that explain to your satisfaction?
Yeah. I just wanted to highlight that there's a number of factors that go into this issue, and that's why people probably need to do a little bit more research themselves rather than sort of just concentrate on what's fed by the media. I mean, I think that's probably helped society a lot and people a lot if they were prepared to sort of do a little bit of their own research rather than be spoon-fed.
Now, I've covered a lot of ground in here, and it's going to be quite a lot to absorb, although you can go and review all this and so on. But if you want to know more about some of these things in detail, then people will have to do some of their own research on things like Milankovitch cycles. I'm going to cover more of these issues in a bit more detail next week, but I can't cover everything. It's a huge topic, and we're taking 2 hours over it, an hour this week and an hour next week as it is, but it's still rather simplified and compressed into that time frame.
Well, I'd like to thank you tonight, Robert, for coming on, and we're looking forward to next week, where we get into some of the nitty-gritty of the conversation that faces society today, and the information we've bombarded with on a daily basis of all the doomsayers, and especially for us people up here in North Queensland, how our reef is dying and it's caused by carbon dioxide, how our lives are going to change because of rising sea levels that are going to flood our coastal cities. So we're looking forward to discussing.
We'll cover all those issues next week.
All right, thanks very much. We'll just wrap it up there. It's been very, very timely. We'll be posting this show up on the various Facebook channels, so you can come and view it anytime you like. We'll also be posting it up to YouTube channel. You can view it there at your leisure. But if you enjoyed the show, please like, share, and follow, and subscribe to the YouTube. Next week, Robert will be back with the second part of the interview. And again, thanks very much.